Since the Industrial Revolution, the world's energy needs have been being met mainly by the combustion of fossil fuels such as coal. This is however bound to change in the coming years, as fossil fuels are a finite resource with ever-dwindling quantities available, as well as the large amounts of pollutants expelled during combustion, which are some of the largest contributors to global warming. In the last few years, there has been a shift in the research regarding energy. Rather than trying to increase the efficiency of the aforementioned fossil fuel methods, alternatives are being sought. At the forefront of these new methods for energy generation is wind power, specifically wind turbines, thanks to them being a renewable energy source. In addition, it is pollutant-free and almost applicable in any environment, unlike some of the competition in alternative energy production, such as for instance solar panels and geothermal energy stations. Energy harvested from wind power covered 11.6% of the energy needs of the EU in 2017, and increased in capacity by 25% the year prior, with a total investment by the EU of 22.3 billion euros. It is because of this that we as hopefully up-and-coming aeronautical engineers were tasked with designing, manufacturing, and subsequently testing such a wind turbine. The challenge had a set of objectives. Our turbine had to maximize the coefficient of power, defined as the ratio of power extracted to the power entering the turbine through the wind. It had to rotate clockwise, at a maximum angular velocity below 3000 rpm. Maximum CP had to be achieved at a tip speed ratio, defined as the ratio of the tip speed omega to the speed of the wind v, determined by us, and had to be in the range of 3 to 8. Lastly, it had to be 3D printed as a single part in a 400 by 150 by 75 mm box. The turbine was to be tested in a closed-loop wind tunnel at 4 speeds, 6, 8, 10 and 12 meters per second. Firstly, we had to decide on the general design of the wind turbine. Specifically, how many blades will our turbine have? 1, 2, 3 or more. Due to technical difficulties, we decided to reject one-bladed design as it was too difficult to balance, and turbines with 4 or more blades were too difficult to make. We were left with either 2 or 3-bladed designs. We researched the literature. For maximum efficiency, the blade should move through undisturbed air. In optimal rotor tip speed ratio by M. Rageb, we found that this time is approximately S over V, where S is half the turbine radius and V is the wind speed. For a turbine with n blades, rotating at angular velocity omega, that time should be equal to 2 pi over n omega, the time needed for the blade to enter the position of the neighboring blade. This, after transformation, gives us a tip speed ratio of 2 pi. Optimal TSR allows us to deduce the optimal rotational speed for the two main designs at 12 meters per second, around 1900 rpm and 1300 rpm respectively. The lack of a third blade, reducing torque, is therefore completely mitigated by the higher rotational speed. Since the airspeeds we were testing at were rather small, a two-bladed design would allow for higher relative speeds at the airfoil sections, and therefore slightly increased performance of the airfoils. Higher Reynolds number gives us higher CL and higher L over D. The 3000 RPM limit was assumed to be far enough not to influence the decision. To further increase operational Reynolds number, longer blades were necessary. We opted for a radius of 390 mm, which was possible by implementing a folding design, which I will describe later. Due to the rotation of the blade, the further away from the root, the higher the speed seen by the airfoil section. This means that the chord length must decrease span-wise to reduce induced drag. Schmidt's theory concerning optimum chord lengths was used to develop a code to produce the blade planform. Due to angular velocity, the effective angle of attack seen by each blade section changes. It follows that the blade must be twisted to ensure maximum effectiveness. We used Betts' theory to compute the required twist. Having established key parameters, we used MATLAB to construct the initial blade design. We could proceed to select the airfoils. Whilst maximum performance was the objective, we had to strike a balance between aerodynamics and structural integrity. To enhance the blade's structural and aerodynamic performance, 3 distinct airfoils were selected. For its high CL over CD and slightly larger thickness over competitors, the E216 was selected for the majority of the blade. Due to the small lever arm and high load, structural integrity was the priority when approaching the root. The E210 was chosen for its performance and thickness for the narrowing section, the S8037 a much thicker airfoil for the actual connection to the cone. Finding a way to reduce drag at the root and the tip was imperative. The root was narrowed down to reduce drag while spinning. The tip was bio-inspired from a hummingbird. This particular species was selected as the high tip speed ratios while hovering resemble ones predicted for our blade. Models with and without the tips were tested in Q-Blade. Results showed the wingtips did marginally increase performance. The nose cone was chosen to be in the shape of the front 16% chord of the S9035 symmetrical airfoil. In order to fit in the given box size, printed as a single part, we designed a folding mechanism with hinges. Our model used a total of 2 hinges, one on the back end of the cone, folding the 2 blades together and splitting the cone in half. Each half of the cone had half of a thread. After folding together, a nut was to be screwed onto it to give structural safety. The hinge was placed on the cone and not on the blades in order to minimize the possibility of failure at an already critical point. The other hinge connected the tip of the cone to the base of the cone, allowing for a rotation larger than 90 degrees, which in turn allowed for a larger radius. This folded on top of the fully set blades and covered the screwing nut. Having this design, we modeled it in the CAD program Creo. The design was complete and the turbine could be manufactured. The manufacture process started with the manufacturing of the metal hub that would connect the turbine to the testing shaft. This was done using a computerized numerical control, short for CNC, technique. We made a keyhole, sanded the edges, and the part was ready. The blades were 3D printed from ABS. Thanks to the structure of the folded design, the strands of the printing material were positioned parallel to the blades. This way, the blades had increased strength in this direction. The 3D printed blades were then sanded to smoothen out their surface and increase their aerodynamic performance. After sanding, the blades were assembled together by screwing in the central nut. Additionally, we attached the turbine to the hub by using 2 countersunk screws, giving our turbine phenomenal structural strength. The last step was to fix the cap onto the nose. We did that using epoxy glue, which, apart from fixing the cap, also helped us fill in the imperfection and voids generated during 3D printing. Finally, the turbine was ready. Next phase, testing. The tunnel was switched on. After giving it a small push, the turbine started to spin and accelerate. Using a brake and torque meter, we measured the power output of the turbine as a function of the wind speed and the angular velocity omega. We did this for the wind speeds of 6, 8, 10, and 12 meters per second. Using an external computer program, graphs were plotted presenting the measurements. After all the measurements were taken, the wind tunnel was stopped and the turbine was dismounted. Firstly, we can comment on the tip speed ratio. Our design TSR was 6.3. The TSR obtained during the test at the maximum power coefficient of 0.408 was 5.843. The percentage error is therefore equal to 7.3%, which is moderate but not substantial, so it can be said that the testing result is consistent with our design prediction. Moreover, at the wind speed the turbine was optimized for, 12 meters per second, the TSR is equal to 6.127, which is much closer to the design TSR, less than 3% off. This, however, came with CP reductions due to increased tip losses. One of the design challenges was to have the TSR between 3 and 8. This was achieved. Another design challenge was that the maximum angular velocity should not exceed 3000 rpm. From this graph, the power generated against the angular velocity, it can be seen that the angular velocity at each test speed was below the specified maximum. Our turbine managed to get a maximum power coefficient of 0.408, which is acceptable performance for a wind turbine. A common problem for wind turbines is resonance appearing at higher rotational speeds. During testing, a large noise did arise at such speeds. However, there was no resonance showing up in the power versus angular velocity plots. This means that although the noise was most probably caused by the turbine, the resonance did not substantially affect its performance. During testing, our turbine did not self-start, so we gave it a gentle tap on one of the blades at about 6 meters per second. Since self-starting is not a design requirement of the project, we did not consider it during our design phase. However, if we wanted to self-start as efficiently as possible, we would have to increase blade area near the root. This part of the root has the least amount of twist, and therefore produces torque also at lower angular speeds. A lot of factors influence performance. The conducted wind tunnel tests had a major flaw, which was blockage. Our turbine was relatively large compared to the dimensions of the wind tunnel. This increased the power of the wind that was entering the turbine, as well as changed the velocity profiles across the turbine. Consequently, this influenced the effective angle of attack. Previously calculated twist was less efficient. This also caused the maximum CP and TSR to be different than what we initially predicted. In order to get more accurate results, a wind tunnel with a greater cross-sectional area should be used. Our design can be improved by taking consideration of blockage effects at the design phase. If we wanted to maximize a CP for the specific wind tunnel test, we could increase the root chords. Additional drag at the root would not be so detrimental due to blockage effects, thus increasing performance of the turbine. Another option would be to conduct tests outside, which would get rid of the blockage effects. The previously mentioned increase in drag could also influence the structural integrity. However, our turbine withstood that test. It could, however, be a problem if we were to influence the blockage to use the blockage for our benefit. This is especially true at the tip where the weakest part of the turbine is located in terms of structural integrity. As for our folding and securing mechanism, it withstood the challenge. The turbine did not fall apart. The securing nut was a quite ingenious idea which proved to work. The only flaw of the mechanism was that our hinges did not survive the manufacturing. Their thickness should have been increased. Both the structural part and aerodynamic part of the design were very good. The folding mechanism fulfilled its objective. However, blockage effects substantially influenced the performance of the wind turbine. Overall, we can say that our turbine was a great success. Alright, that's all folks. Thank you very much for listening and I hope you enjoyed our presentation.